Hey everyone. So in this video, we're going to be doing part two of our computational methods homework, or remember part 1B of our computational methods homework. Um, disc- uh, Derive the expression for entropy of a discretized probability distribution, right? Um, so let's suppose, right, we have, or let me actually make this a brush or marker. Let's suppose we have n students in a classroom, right? And they take a test, okay? And they get a grade, right? So when you as a teacher you report those grades, you're going to report how many people got a certain grade, right? So how many people got a certain grade will say NI, where I is the grade sort of bracket that you're going to be talking about, right? And so if you were to find so when we say the total entropy of a system, what we kind of mean here is just um, like how many people or how many different pathways or combinations you can get. So for us, it would be how many different combinations you could get of students, like students in different grades, right? And we're going to actually use, and so here to write the number of permutations, because order doesn't matter, we're going to say it's n factorial divided by all of the little n factorials multiplied together. So ni factorial, and then it's going to be, they're all multiplied together. So this is just a symbol of multiplication for like a the analogous of summation, but for multiplication instead of addition, right? And so we have this permutation, and so we can't really maximize it because factorial is so big that our like Python won't be able to handle it if we try to maximize it. Uh, this should be erased. Um, let's just erase that. We don't want to spoil. Um, yeah, we don't want to spoil the future. So we might have seen it there, but we're going to use what's called Stirling's approximation. Stirling's approximation is this: if you have ln of n factorial, it equals n ln of n minus n, right? And so Stirling came up with this. It's really, really useful for a lot of stuff in statistical thermodynamics if you ever have the pleasure or misfortune of taking that. Um, but here we can just take a natural log of our permutations to generate a maximizable function, right? And so if we do that, first let's simplify this using log rules. Yeah, so it's just simplify this using log rules and then apply Stirling's approximation. So here we're going to say is equal to n log n minus n minus, and then for this one, when we apply Stirling's approximation, right, we have the multiplications, the multiplicative sum or product uh, of n factorial, right? And so if you think about that, that's basically multiplying a bunch of natural logs together. Or it's basically multiplying all of the ni factorial terms together, right? And we know that if we have two things multiplied in a natural log, you can separate them by adding. So if you have ln a b, it's ln of a, sorry, a plus ln of b, right? And so let me erase this guy. So here you can basically turn that multiplicative thing into a summation of ln's, right? So we're going to sum, and then we're going to apply Stirling's approximation. So we're going to say it's n log n minus n. All right. And so to simplify this, one main thing, right, is the summation of the number of students in each bin, right, or each like grade range that you have. It's just going to equal the total number of students eventually, right? Because I mean, it's just all the students who took the test. So these two terms can cancel, and then you get equal to n log n minus the summation of n log n, right? And essentially here, this is a constant. So what we want to do is maximize this summation or minimize the negative of that summation, right? And so we take the summation n log n. And so in the problem, they wanted us to talk about it in terms of discrete probabilities, right? And so if you think about it, n is the number of students that say got a 50%, right? How would you write that in terms of the total amount of students? You would simply say n, the number of students who got a 50% is the probability of a student getting a 50% times the total amount of students, right? And so we can make that substitution here. So this becomes the summation of uh, pi n. Sorry, these should be ni's, I think. Yeah, pi n. Oh, and I've made a mistake. All of these logs should be ln's. That if I wrote log up here, I apologize. It should be a natural log because we've been using that. So it should be the summation of pi n times the natural log of pi times n, right? And then we're going to take the big N out of the summation because it's constant, right? So you're going to get n times the summation, and then let's split up our natural log. So it's going to be probability times ln of pi plus probability, ln of n times pi, right? And let's analyze this term. So the summation, so this is constant, right? So the only thing that varies with our summation is the pi. And then the summation of the probability over all discrete probability values is going to be 1, right? All probabilities values need to be 1. So essentially, this value is constant. It's just a natural log of n. So when we talk about things that vary with our probability distribution, this is just a constant. We don't need to worry about maximizing that. This is what we need to maximize. And in the same vein, this doesn't matter for us either because n is going to be constant regardless of the distribution. So the function for entropy that we need to maximize is the summation of the discrete probabilities over all of the all of the probabilities, right? Um, times the natural log of each probability. And if we can maximize this summation or minimize the negative of it, we can maximize the entropy of our system, which we will be doing in the next part. All right. Thanks, guys. Have a good one. Bye bye.